In this lecture, I am going to discuss the displacement analysis problem for robot manipulators. The overview of today's lecture is as follows. We will look at the displacement analysis problem, the problem of forward and inverse kinematics with examples of RR and RP open chain manipulators. These are planar open chain manipulators. So, we are going to look at the forward and inverse kinematics problem for these manipulators. So, our plan is that we are going to look at the planar robots open chain, then subsequently we are going to look at closed chain planar robots. As already discussed before, the forward kinematics and the inverse kinematics problem for kinematic chains is that in the forward kinematics we are given the inputs or the joint angles, maybe joint displacements, and we have to find out the output motion. The inverse kinematics is just the reverse. We are given the end effector position and maybe orientation, and we have to find out what should be the actuator displacements. We are going to look at these two kinds of chains, open chain manipulators. One is 2R, the other is RP. Later on we are also going to look at 3 degrees of freedom kinematic chains. So, this is an RR open chain manipulator. So, the forward kinematics problem is as follows. We are given theta 1 and theta 2, which are these joint angles. Note how theta 1 and theta 2 are defined. Theta 1 is defined from the x axis to link L1, and theta 2 is defined from link L1 to L2. Now, given theta 1 and theta 2, we have to find out the position of the end effector. So, that is the forward kinematics problem. You can very easily write out the location or the position of the end effector, which is denoted by xc and ye. For example, this xc, so this is xc, this is nothing but the sum of these two lengths. This length is L1 cosine theta 1, and this length, this angle is theta 1. So, this length becomes L2 cosine of theta 1 plus theta 2. That gives us xc. Similarly, you can find out ye as L1 sin theta 1, which is this length, and add to that this length, which is L2 sin of theta 1 plus theta 2. That gives us ye. The end effector orientation coordinate given by this angle phi is theta 1 plus theta 2. So, the forward kinematics problem is fairly straightforward. Let us look at the inverse kinematics problem now. We are given xc and ye, which is the location of the end effector. We have to find out these angles theta 1 and theta 2. We start off with the forward kinematics relations, x c in terms of theta 1 theta 2, similarly y e in terms of theta 1 theta 2. Then we are given x c and y e, we have to find out theta 1 and theta 2. If somehow I can eliminate this sum of theta 1 and theta 2, then I can get a relation only in terms of theta 1, which is shown here. What I do is take it to the left hand side, the first term, and square and add. That will give us L2, that eliminates theta 1 plus theta 2. So, therefore, we have a relation between theta 1 and the other known quantities. Now, this can be expressed. So, this was our equation after eliminating theta 1 plus theta 2. This can be recast as a sin theta 1 plus b cosine theta 1 equal to c, where a is y e, b is x c and c is this expression. This can be very easily derived by simplification. Now, this kind of equation we have solved before. Once we have solved for theta 1 from this equation, we go back to these two equations. We have taken this to the left hand side. Now, we will take the ratio to find out tangent of theta 1 plus theta 2, and that is given by y e minus L 1 sin theta 1 divided by x c minus L 1 cosine theta 1. Since theta 1 is now known, we can find out theta 1 plus theta 2, and once we can find out theta 1 plus theta 2, and since theta 1 is known, we know theta 2. Now, this is a solution procedure that we have discussed already. For this kind of equation, we substitute x as tan theta 1 by 2, write out sin theta 1 and cosine theta 1 in terms of x, substitute them back in our equation, obtain the quadratic equation, and finally, we have the two solutions given by these two signs. So, we have tangent theta 1 by 2 given by this expression in terms of a, b and c, which are known. Therefore, we have two solutions of theta 1, theta 1 1 and theta 1 2. And once we have theta 1 1 and theta 1 2, we can substitute in this expression for tangent of theta 1 plus theta 2 and determine theta 2. When we take these tangent inverses, here also we have to take tangent inverse, we must use the a tan 2 function to get the correct quadrant. Let us try to understand the two solutions graphically. These are the two solutions. Now, what is fixed is this point x c y e, that is fixed. Now, these two solutions can be thought of as the assembly of this manipulator at these two positions. This hinge as considered on L2 will move on this circle, and the same hinge as considered on L1 will move on this circle. Therefore, the mechanism can be assembled at the intersection of these two circles. There are two intersections, one is shown here already in black, the other configuration is this red configuration. So, these are the two configurations which will reach the same point x e y e. Next, let us look at the theoretical workspace of the manipulator, where this manipulator can reach. As you can see, this joint, if it can rotate 360 degree, then this hinge will rotate on this circle. In the same way, when this joint rotates completely, the end effector will rotate on the smaller circle. Therefore, the reach of the manipulator is now shown here. It is within this blue region, it can reach anywhere within this shaded region. This is the workspace of the manipulator. Next, let us move on to another kind of planar open chain manipulator, the RP. This also has 2 degrees of freedom. The degrees of freedom here are this angle theta and this extension of this prismatic pair, which is indicated by this S. The angle alpha is a fixed angle. This angle is fixed. Therefore, we have 2 input variables, one is theta, the other is S, which will position the end effector, and the coordinates of the end effector are given by x e y e. The orientation of the end effector is given by this angle phi. The forward kinematics problem is finding x e and y e when we are given theta and S. Let us look at these relations, the expression of the coordinates which are straightforward. X e, so this is x e, is a summation of these two lengths. This is L1 cosine theta 1. Now, this is S times, this is theta 1, this is theta, well this angle is theta, so this angle is theta and this angle is alpha, which is fixed. Now, since all angles we will be measuring counterclockwise as positive, which is by our choice of coordinate system. So, counterclockwise measurement of angles is positive, clockwise measurement is negative. Therefore, this angle is theta minus alpha, and therefore, this distance is S cos theta minus alpha. So, that is the total x e. Similarly, you can express y e as L1 sin theta and add to that this distance, which is S sin theta minus alpha. So, the angle will take care whether it is added or subtracted. As you can see, theta minus alpha will be something negative and sine of negative angle is negative. So, this ultimately gets subtracted from L1 sin theta. Therefore, that gives us the y coordinate. The end effector orientation coordinate, which is phi, is theta minus alpha. So, once again the forward kinematics problem was straightforward. Let us look at the inverse kinematics problem now. In this, we are given x e y e, which means we are given the location of the end effector. We have to find out theta and s, this angle and the throw of this prismatic actuator. Since we have two variables, 2 degrees of freedom, we can fix the location of the end effector. Let us again start with the forward kinematics relations, which I have written out here. X e in terms of theta and s. Here you must remember that this angle alpha is fixed. What we have to determine are theta and s. What we do in the first step is eliminate s. So, to eliminate s, we take this first term from the right hand side to the left hand side and divide. So, we come to this expression. This can be simplified to obtain an equation of this form. Where a, b and c are known, since x e, y e these are given to us. Therefore, a, b and c are known, we have to solve for theta. Once we solve for theta, we need to find out s. To do that, we multiply the first equation with sin theta and the second equation with cosine theta, and we subtract. If you subtract, these two terms cancel off, and therefore, you are left with x e sin theta minus y e cosine theta, and this simplifies to s sin alpha. Here everything is known except s. Therefore, we can solve s. Let me directly show you the solutions. These are the two solutions that we obtained for theta, theta 1 and theta 2. These are the two solutions of theta depending on the sign that we consider here, and corresponding to the two values of theta, we will get two values of s. Once again, for the tangent inverse, we need to use a tan 2 for the correct quadrant. Let us try to understand the solutions, the two solutions that we have obtained. I have written out the solutions here. In this inverse kinematics problem, we were given this x e and y e, this was known. We had to find out this angle theta and the throw of the actuator. Now, here I have drawn a circle which is tangent to the line of sliding of the prismatic actuator. This is the line of sliding of the prismatic actuator, and this circle is the tangent circle centered at the origin. So, the base of the manipulator. Now, we draw this tangent, and that must be the second link, and the first link is obtained because we know this angle alpha. So, these two values we know from the solution. The other solution, that since we have two solutions, as you can see, the other solution is obtained by drawing a tangent to the circle from the same end effector point. We have two tangents to this circle, one is shown in red, the other is shown in blue. In order to now locate the link L 1, we draw this line such that this angle is alpha. Now, this second solution is unphysical as far as the physical construction of the manipulator is concerned, because you will note that the end effector has gone on the reverse side. The end effector has gone on the reverse side, which is not possible to achieve in a physical manipulator, though this is a mathematical solution. The end effector reaches the desired point x e y e, but it is physically not possible for a single manipulator to achieve these two solutions. So, this is a different manipulator altogether, where the end effector is on the other side of the prismatic pair. So, these are the two solutions that we obtain from the inverse kinematics problem. Now, the workspace here, as the joint 1 rotates 360 degree, this is the theoretical workspace. As it rotates 360 degree, this point can move on this circle, and the throw of this actuator will, the maximum throw of this actuator will decide what is the reach of the manipulator, what is the outer boundary of the workspace. So, this gives us the workspace of this manipulator. So, this blue shaded region is the workspace of the manipulator. It cannot reach at any point here or any point here, given that this is the S max. So, let me summarize. We have looked at the displacement analysis of planar robot manipulators. We have looked at two examples, the RR and RP manipulators, discussed their forward and inverse kinematics, and we have interpreted the solutions and looked at the workspace of the two manipulators. With that, I will conclude this lecture.